9.5 Interference of light waves. Young's double-slit experiment. If light travels as a wave, then it should interfere like a wave. Experiments looking for interference with light failed because, number one, light waves have extremely small wavelengths and higher frequencies compared to water waves that were studied in detail. Water wavelengths comparatively are large and their frequencies are small. And light has no fixed phase and therefore is defined as incoherent. Physicists found that if you pass monochromatic light, which is light of a single color, through a narrow slit, it acts as a single point source and therefore acts as a coherent wave. At the very end of the 1700s, Thomas Young performed a series of experiments to determine what happens when light passes through two closely spaced slits. We now refer to his basic setup as Young's double-slit experiment, and it demonstrated conclusively that light behaves as a wave. The experiment also provided a method to measure wavelength. When light passed through two small slits, each slit acts as a point source. An interference pattern of alternating bright and dark fringes was produced. So when monochromatic light, such as laser light, passes through the slits, the laser light hits the screen on the right and produces an interference pattern. And this arrangement satisfies the general conditions required to create wave interference. And we saw these general conditions in a previous lesson when we determined the interference patterns produced in water waves. So the general conditions, as a reminder, state the interfering waves travel through different regions of space. In this case, they travel through two different slits. The waves come together at a common point where they interfere, in this case, on the screen. And finally, the waves are coherent. In this case, they come from the same monochromatic source. We have three definitions. The first is interference fringe. It's one of a series of alternating light and dark regions that result from the interference of waves. Maxima is a point of brightness or maximum of intensity in an interference pattern, and minima are the points of darkness or minimum intensity in an interference pattern. Here we have two diagrams. In the first diagram, we have two slits, and they are located a distance of d apart. We're measuring the distance L1 from slit number 1 to a point P on the screen, and L2 is a point from slit number 2 to the same point P on the screen. The difference in their lengths, the difference between L1 and L2 can be given this trigonometric relationship where delta L is equal to d sine theta. And we mentioned that d is the distance between the two slits. In the second diagram, we show what happens when the screen is very far apart. And this setup helps us to further understand and develop equations. The most important thing for us to gather from this is that we can make the approximation that theta is constant in all of these diagrams. Okay. In order to do well in this section, you need to compare the equations that we have to these diagrams above and be able to label and properly give the appropriate term or symbol for each of the labels on the screen. Let's look at the first set of equations. In order to determine the maxima, areas of constructive interference, when two waves arrive in phase, we have the equation d sine theta m is equal to m lambda, where m represents 0, 1, 2, or 3, and so on. These are the different orders of maxima. For example, the center maxima is called the zero order maxima. The next maxima to the right or the left is called the first order maxima, and so forth. For m equals 0, 1, 2, 3, etc., in this notation, m equals 0 denotes the maxima in the center of the screen. We also have an equation for the minima. Areas of destructive interference when two waves arrive in opposite phase. And this equation is d sine theta n is equal to n minus 1 over 2 lambda, where n equals 1, 2, 3, etc. These are the minima. These dark lines or minima are called first order minima, second order minima, and so forth, and they occur on either left side or right side of the zero order maxima. Here's a diagram showing the zero order maxima, this point right here, which happens at the center between the two slits. We have a couple other quantities that we need to be familiar with. The distance from the slits to the screen is capital L. And the distance between the maxima, we give the symbol x. And if you take a look, the subscript number 1 represents the first order maxima, the distance from the zero order maxima to the first order maxima. In general, the distance from two maxima should be the same throughout this diagram. So we have an equation that allows us to find the change, delta x, the separation distance between the bright fringes on the screen. And that's our first equation for our bright fringes. Our second equation for the mth order bright fringe becomes x subscript m is equal to m L lambda over d. Again, where m is the order 0, 1, 2, 3, etc. L is the length between the screen and the slits, and d is the distance or separation between the two slits. We also have an equation for the separation distance of dark fringes. And it states that the separation distance of each dark fringe from the center of the screen can be found and is equal to xn. Xn is equal to n minus 1/2 L lambda over d. And we use this equation where n is 1, 2, 3, and so forth. Let's try a sample problem. A double slit experiment is carried out with a slit spacing of 0.41 millimeters. The screen is at a distance of L equals 1.5 meters. The bright fringes at the center of the screen are separated by a distance delta x equals 1.5 millimeters. Calculate the wavelength of light. So, if we do this, we have d equals 0.41 millimeters. And we want to change that into meters. So it becomes 4.1 times 10 to the power of negative 4 meters. We know the screen is at a distance of 1.5 meters from the center of the screen. And the bright fringes are separated at a distance of 1.5 millimeters, which is 1.5 times 10 to the power of negative 3 meters. Our job is to find lambda. So we're going to use our equations and determine which equation is the right one to use in this situation. We know that delta x over L equals lambda over D. Rearranging for lambda, we get lambda is equal to D delta x over L. If we sub this in, we get 4.1 times 10 to the power of negative 4 meters times the separation of the bright fringes we said was 1.5 times 10 to the power of negative 3 meters. And the distance from the screen to the slits is 1.5 meters. If we punch this into our calculator, we end up with a wavelength of 4.1 times 10 to the power of negative 7 meters. Sample problem number 2. Determining slit separation. The third order dark fringe of a 660 nanometer light is observed at an angle of 20 degrees when the light falls on two narrow slits. Determine the slit distance. So we know that since it's the third order, n equals 3, the wavelength is 660 nanometers. That is 6.60 times 10 to the power of negative 7 meters. And theta subscript 3 is 20 degrees. And we want to find D. So we're going to use the equation. From up above, for the dark fringe, this one right here, which states that d sine theta n is equal to n minus 1/2 lambda. So d sine theta 3 equals, actually I'm just going to use n for this general example, n minus 1/2 lambda. So solving for d, we have n minus 1/2 lambda over sine theta n. We can sub and solve. We have 3 minus 1/2 lambda is 6.60 times 10 to the power of negative 7 meters over sine theta 3 is 20 degrees. If we punch this into our calculator, we end up with a separation distance between the slits that is equal to 4.8 times 10 to the power of negative 6 meters. You'll be able to see quickly that solving these questions for the double slit experiment is relatively simple, provided that you know what each of the symbols in all of the equations stands for. Now, another interesting development in the theory of light. Young's evidence for the wave nature of light was not accepted by the scientific community until much later, until the year 1818 when Augustin Fresnel proposed his own wave theory, complete with the mathematics. A mathematician named Simon Poisson showed how Fresnel's equation predicted a unique diffraction pattern when light is projected past a small, solid object as shown. Poisson's argument was that if light behaved as a wave, then light diffracting around the edges of the disk should interfere constructively to produce a bright spot at the center of the diffraction pattern. This was impossible according to the particle theory of light. But in 1818, Poisson's prediction was tested experimentally by Dominique Arago, and to many people's surprise, he successfully observed the bright spot. Arago's experiment demonstrated what is now called Poisson's bright spot. For homework, I'd like you to try practice problems on page 482 and review questions on page 484.